In this video, we're going to explore the ideal gas law, which relates pressure multiplied by volume is going to be equal to the number of moles multiplied by a constant times the temperature. So these five variables are going to be related. Well, R is not a variable, R is a constant, which we'll talk about. But first of all, what is an ideal gas? An ideal gas is this hypothetical gas where the molecules are thought to not occupy any space. Like, it's not considered that the molecules occupy the space. And since the molecules don't interact with each other, this ideal gas behaves perfectly and it follows the gas laws ideally, perfectly. So all the laws that we saw in the combined gas law video are followed to perfection. So at standard temperature and pressure, which is called STP, standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere, scientists observed that an ideal gas, 1 mole of that ideal gas, is going to occupy 22.4 liters. Okay? So if we have all these variables together, what we need to do is, let's put them into the formula to determine R. So if we algebraically manipulate this, we're going to get that R is going to be equal to PV divided by NT, where pressure is 1 atmosphere, where volume is 22.4 liters from that observation, and where the number of moles is 1 mole of that ideal gas, whichever it may be, at a temperature of 0 degrees Celsius. But since we can't put 0 here because that would not allow us to work it out mathematically, remember, any gas law problem, whether it be ideal or combined, we need to convert our temperature into Kelvin by adding 273.15. So this means that the actual temperature we're using for this problem is 273.15 degrees. Well, not degrees, Kelvin, okay? So if we were to punch that into the calculator, we're going to get the value of R. And this is quite relevant because this is going to help us to solve most of our problems, okay? So in this case, R is going to be equal to 0.0821. You will find it like this in a few textbooks. It's rounded up in a sense, but really remember that R is given either by your teacher, or it's given in the problem, or you're asked to calculate it. And as long as we're all consistent with the theory that at STP at 0 degrees Celsius, 1 atmosphere, 1 mole of gas occupies 22.4 liters, we can calculate R, whose units are atmospheres times liters over moles times Kelvin. So this is a piece of information we're always going to know. Now, how does this work? How do ideal gas law problems go? Let's try to solve one of those problems where we're always going to start with PV equals nRT. We write an inventory, PV nRT. We always know that R is 0.0821 and their units are atmospheres, liters, moles, Kelvin, meaning that we have to turn all our units into these units in order to be able to work out the formula. So let's say it says a sample of nitrogen gas is kept in a container with a capacity of 2.9 liters. 2.9 liters is volume, so we're going to write it here, 2.9 liters, at a temperature of 308 Kelvin. And the pressure is 5.2 atmospheres. The question is, calculate the number of moles in the container. And we know that it's nitrogen, but this is just additional information. We're asking how many moles, X moles. We check to see if the units are consistent. So atmospheres, atmospheres, liters, liters, moles, moles is our incognito, Kelvin, Kelvin. So now our incognito is N, which is right here. And from the algebra, we know that N is going to be equal to PV, but we're going to take R and T and we're going to pass them to the other side, dividing R and T. We can just plug in our numbers right here, and the number of moles is going to be equal to pressure, 5.2, and the volume is 2.9 liters, over R, 80821, and the temperature is 308 Kelvin. So this problem was very nice. They gave us all the values just as is. We don't even have to convert the units. And our final answer is, we're going to get 5.2 times 2.9 times 0.0821 times 308. Let's see, 5.2 times 2.9 divided by 0.0821 times 308. And we get our answer, which is 0.60 moles of nitrogen are contained in this specific tank or container. So this problem was really straightforward. Let's look for another problem. And again, let's see. It says, how many grams of helium are there in a balloon? So grams of helium, that sounds a little bit tricky, but it really is not tricky, because we start out with our formula, nRT. And the question is, how many grams? So how would we explore this question? Let's see, let's first fish out all the variables. How many grams of helium is the identity of our gas, are there in a balloon that holds 9.3 liters of this gas at 15 degrees Celsius and at 950? Oh, I'm sorry, I made a mistake right here. This is volume and this is pressure. At 15 degrees Celsius at 950 millimeters of mercury. R, we know it's 0.0821 atmospheres, liters, mole, Kelvin. And the number of moles is unknown, but it's asking us for the grams of helium. However, we already know how to calculate that. From moles, we can convert to grams using molar mass, which will be our last step. First, let's convert all our units, and let's see. Atmospheres, the pressure is not in atmosphere, so we need to convert that, and we know that 760 millimeters of mercury is 1 atmosphere. So we punch that into the calculator, and we get 950 divided by 760. We're going to get 1.25 atmospheres. So now they're matching. Liters, we're in liters. It's good. This is good. Moles is our incognito. Kelvin, this is not in Kelvin. We need to convert it by adding 273.15, and we're going to get 287.15. Now, since what is incognito is N, once again, we know that N is equal to PV divided by RT. And once we plug in these values right here, we're going to get that P is 1.25 atmospheres. Volume is 9.3 liters over 0.0821. I didn't write the units because we know they're right here. And at the end of the day, we're going to add temperature, which is 287.15. So we multiply all of that in our calculator. And we're going to get, 288. Because that will give us a little difference right here. So we say 1.25 times 9.3 divided by 0.0821 times 288.15. And we're going to get N is equal to 0.49 moles of what? Helium, which was given. That's not our final answer because it's asking us for grams, so we would reach for our periodic table. But let's just say, for argument's sake, that we know that 1 mole of helium, which is not diatomic, it's a simple, it's a monatomic gas, is 4 grams per mole of helium. So moles cancels out, and our answer is 4 times 4 times 0.49, and the answer is 1.96 grams of helium is the answer of what's contained. So as you can see, this is pretty straightforward. We're going to solve another one for this final installment. And once again, be very methodical. This really helps you in understanding the problems. PV equals nRT. We set up our inventory. PV nRT equals, we know that R is 0.0821 atmospheres, liters, moles, Kelvin. And this way we can engineer everything out and we can just solve really simply. So it says, calculate the volume of a tank that stores 330 grams of carbon dioxide at 3 atmospheres and 22 degrees Celsius. And volume is going to be given in liters. This is what we're being asked. How much volume will we need for 330 grams of carbon dioxide? So why am I putting the 330 grams of carbon dioxide? I'm putting it here because from this, we can get the number of moles, and then it's just solving the problem, okay? So we're going to do a conversion factor here. We need the molar mass, and we need that. We know the carbon weighs 12.01 plus a double oxygen, which is 15.99 times 2, and the molar mass is 43.99 grams in 1 mole. This cancels out, so we'll get 330 divided by 43.99, and that gives us 7.5 moles of carbon dioxide. So our incognito is volume. Volume is right here. We're just going to divide by pressure. Volume is equal to nRT divided by P. And again, this might be the most difficult part in the sense that you need to understand how to work out the problems and do your algebra. Otherwise, you're in deep trouble. And let's see. Let's do our check of units to see if everything is in correct units. Atmospheres, yes. Liters, that's what we're going to get. Moles, we already have it. And then Kelvin, we don't have it in Kelvin, so we add 273.15. And this turns into 295.15 Kelvin. So we're going to plot this into the formula, plug it in, 7.5 moles, 0.0821 with all its units. Temperature is 295.15, and the pressure is 3 atmospheres. So once everything cancels out, our answer is going to be given in volume, in liters, 7.5 times 0.0821 times 295.15 divided by 3. And the answer is 60.58 liters. This is our final answer. So let's have a little recap. And let's remember that the ideal gas law relates pressure and volume equals number of moles times a constant, ideal gas law constant, times temperature, where the ideal gas law constant is 0.0821 atmospheres times liters moles times Kelvin, making it necessary for us to do what? Remember, always convert all the units. In the first problem we saw, they were already harmonized with the units of the R we used. And in the second problem, we were given degrees Celsius, which we converted to Kelvin, millimeters of mercury, which were converted to atmospheres, so that we can plug it into the problem after we do the algebraic manipulation, and we get our answer, right? And again, in the last problem, we were given grams. We converted those grams into moles, and then we harmonized all the units, including temperature, into Kelvin, and we just plugged it in. So that's really what the ideal gas law is about.